As an example, let's say we have a free projectile following this not very well drawn parabolic path. We have some reference point here from which we're measuring the positions along this path. So I could have a vector from here to here, vector from here to here, vector from here to here. Now, for a projectile, if we assume that the projectile started at a point 0, 0, our r of t function would be something like vxt times I plus -1/2 gt squared plus v naught yt j. We would probably have some also x naught and y naught within the two components, but I haven't bothered taking the board space to write them in. Those will arise if you simply set up the conditions of the problem and apply the initial conditions. So this is what we get. This is the kind of thing we could get by analyzing a free projectile. So how do we get our velocity and acceleration functions? Well, this is just the derivative of this. The derivative of vxt is vx. The derivative of -1/2 gt squared plus v naught yt is -gt plus v naught y, and you can check that very easily. And if we take derivative of our velocity function, this being constant, we get a derivative 0, so there's no I component. Derivative of v naught y is 0, but the derivative of -gt is -g, so we get acceleration equals -g times j, times the j vector. Okay, now I've drawn velocity vectors at 3 different positions. This one doesn't look like I did a very good job of making it tangent to the curve, but I should have. It looks like for sure this vector is longer than this one, and this vector looks like it might be somewhat longer than this one. And that's kind of what we would expect, because as a projectile falls, it does seem to speed up. But let's verify that that's true if our model is correct. Okay, well, for this particular time, here's our position vector. Here's our velocity vector. Didn't leave myself much room, but that's kind of endemic. Okay, here's our v of t velocity vector. So here's our r of t vector, here's our v of t vector, and here's some commentary. Okay, we can draw those vectors again. So here's our r of t. Now remember, r of t could be measured from any reference point. We set up our coordinate system, and we generally measure r of t from the origin, although that wouldn't be consistent with the fact that I've assumed that the particle starts at the origin. It clearly didn't. Little contradiction, but don't worry about it. It's not particularly important in this part of the discussion. Okay, so there's our r of t vector, and here's our v of t vector. At some time, some arbitrary time t. And we have our acceleration vector. Now, where does our acceleration vector go in this picture? Well, the acceleration is -g times j. And it's going to be the same for every one of these velocities. As a matter of fact, it's not changing in time. So we just draw our acceleration vector. Again, acceleration's on a scale different than the velocity scale, which is different than the position scale. So we could really draw these 3 vectors at any lengths we wanted. Although having drawn them for this time, if we wanted to draw them for this time, we'd want to keep them in relative scale with the ones that we drew the first time. Okay, we're free right now. We can draw it any way we want. Here's -gj, and that's our acceleration vector. It's acceleration at t. I didn't put the t in because I didn't have enough room. Probably should have to be consistent, but there is no t dependence. Okay, now what's going on with the velocity of this particle at this instant? Is it speeding up? Is it slowing down? We kind of think it's speeding up because we kind of think that things speed up as they fall. But remember, it's moving in this direction as well. Let's take the acceleration and velocity vectors and treat them as we did in the preceding in class. Okay, so here we have our acceleration vector and our velocity vector. They're functions of t, but I'm not going to clutter up the board by doing that, not by putting the t in. But we calculate the acceleration, or we represent the acceleration vector. We'll be able to calculate it in a minute. We represent the acceleration vector in terms of its components parallel and perpendicular to the v vector, to the path of the v vector, to the line of the v vector. So what do? We project the acceleration over here onto the v vector, and we get our parallel acceleration. And then we'll talk about how to calculate this in a minute. I'll probably mention it in a second. We project the acceleration vector onto the line perpendicular to the velocity vector, and we get our A perpendicular. Now, A parallel is in the direction of V. So this tells us that our projectile is speeding up. And A perpendicular is to the left. That's our centripetal acceleration. Changes the direction of motion. That's the only effect it has. It doesn't speed the object up or slow it down. It simply changes its direction of motion. So from this picture, we can verify that the particle is speeding up. And that's going to be the case anywhere on this curve, the curve as I've drawn it. If we want to draw the acceleration vector, we could draw it here. We could draw it here. It's going to be identical. We could draw it here. Let's see how close I came to identical. It's not great, but it's okay. All right, so we have the acceleration vector, which is the same at every point. And in every case, the projection of the acceleration vector on the velocity vector is in the direction of the velocity, meaning that the particle is always speeding up. Now, that wouldn't be the case if the particle was rising. Let's say the particle is rising here. Then we're going to have a velocity in this direction. We're going to have an acceleration in this direction. And the component of the acceleration in the direction of the velocity, well, I guess we project it over here. It's going to get messy. Project the acceleration on the velocity, we see that the component is going to be in the direction opposite velocity. The perpendicular component is going to be like this, which is going to turn the particle, in every case, in what would be a counterclockwise direction according to this picture. Okay? Now, how would we calculate these quantities? Well, A parallel equals the projection onto V of the A vector. Okay, the magnitude of the projection onto V of the A vector is just A dot V divided by the magnitude of V. And that just goes back to the triangles. We've done that before, so you might have to review that, but make sure you understand why that is. Don't just memorize this as a formula. Understand it. It's a simple picture. We've got this triangle here. The dot product is the magnitude of this vector times the magnitude of this vector divided by the angle between them. This should be divided by the cosine of the angle between them. The magnitude of this projection should be the magnitude of this vector times the cosine of that angle, which is what you get if you divide the dot product, magnitude of A, magnitude of B, cosine theta, by the magnitude of V. Now, I just said that, and if you don't understand words real quickly, I don't particularly myself, you probably have to write it out. You want to be sure you lock that in. You want to be sure you understand that. Okay, so we got A dot V over magnitude of V. That's the magnitude of the projection. The projection is equal to the magnitude of the projection times the unit vector in the direction of A. So that's A dot V. I think I said direction of A, it's direction of V, times the unit vector V over magnitude of V. Now you got a handy little formula. You probably use it in vector calculus. You shouldn't need it. You should always be able to derive it. It's a fairly simple picture, just relies on a triangle and a little bit of common sense. You're better off, you're going to remember it, and you're going to understand what you're doing much better if you think it through rather than just use the formula. I'll keep raving about that probably forever. But of course, you always get to the point where you don't quite understand, but you need to get an answer, and you use a formula. Now, every engineer does that at some point, and every physicist does that pretty much at some point, or almost every physicist. Maybe not so much in their own field, but in different fields. Don't always have time to totally understand everything. Okay, well, there's our projection vector, and the projection's easy to calculate. We just dot A with V. What's that? It's going to be G times negative G times negative GT plus V naught T. It's going to be G squared T minus V naught G. And then we divide that by the magnitude of the V vector, and we get the parallel component of the acceleration. To get the perpendicular component, we've done vector pictures that justify this. I'm just going to write this down, and I'm going to let you worry about it. If you look at this picture, it should be pretty obvious that A perpendicular is A minus A parallel. Here's how you get A parallel. You subtract A parallel from A, you get A perpendicular. It's right there in this picture. Make sure you understand that.